Welcome to The Explainer. Today, we are literally going to build a brain. But, not the squishy kind. We're talking about a brain built entirely out of code. This is all about artificial neural networks.
So what if you could do that? Build a brain just using code. It sounds like something straight out of a sci-fi movie, right? But this question, this very idea, is the bedrock of a whole field of technology. It's the core concept behind what we call artificial neural networks, or ANNs for short.
I mean, just think about how your brain works. It's this amazing machine that spots patterns, learns as it goes, and tackles problems without needing some rigid step-by-step rulebook. Well, that's the whole goal here. An ANN is basically our attempt to copy that amazing biological blueprint, but in the world of computers.
All right, so how on earth do you even start building a brain from code? Well, it turns out it all begins with a pretty straightforward, but really powerful basic structure.
So any piece of info the ANN looks at goes through this three-stage process. First up, you've got the input layer. This is like the brain's eyes and ears. It's just taking in all the raw data from the outside world. Then that data gets passed to the hidden layers. Now this is where the magic happens. It's the thinking part, the black box, where all the heavy lifting and pattern spotting goes on. And after all that processing, we get to the output layer, which spits out the final answer.
Okay, this is where things get really interesting. Let's talk about how this network actually thinks. To get that, we need to zoom in on what's happening inside those hidden layers. It's not just data flowing through a pipe. Oh no, there's a whole decision-making process going on at every single connection.
So every single connection between these artificial neurons gets what's called a weight. Just think of it like a volume knob. A higher weight means the network turns the volume up on that piece of information. It's super important. A lower weight, it's less influential, kind of like background noise.
It's almost like a tiny election inside each neuron. Every bit of incoming information gets to vote, and its weight determines how many votes it gets. The neuron's job is simple. It just adds up all the votes. The final tally gives it a single number that represents the total strength of all that incoming info. But here's the kicker. The neuron doesn't just mindlessly pass that number along. Nope, it takes that final score and runs it through one last check, something called an activation function. And really, this function is just a simple on-off switch. It's the bouncer at the club door deciding who gets in and who doesn't.
It's a really simple deal. If the signal is strong enough, if it crosses a specific threshold, bam, the neuron fires. It passes the message on to the next layer. But if the signal is too weak, it stays silent. The message stops right there. Now imagine this simple fire or don't fire decision happening millions of times, all at once. That's how the network learns. That's how it makes incredibly complex choices.
Okay, so because they're built this way like a brain, ANNs have some serious superpowers. We're talking about abilities that your typical old-school computer program could only dream of.
For starters, they can multitask on a massive scale. That's parallel processing. And their memory isn't stored in one fragile place, it's spread out all over the network. And this is what makes them so tough. Think about it. A regular program hits one tiny error in its code and it just crashes. Game over. But an ANN? It's designed for the real, messy world. A few neurons can die, some of the data can be garbage, and the network just keeps on ticking. It's built to be resilient.
So, what are these things actually good for? I mean, they're not a silver bullet for every problem. But for a very specific kind of challenge, they are absolutely in a league of their own.
You want to use an ANN when your data is a total mess. Noisy, complicated, maybe even full of mistakes. They're perfect when you need an answer fast, and you're okay with it taking a good long while to train the model up front. But take a look at that last point on the list. This one's important.
Yeah, that one. It says it's not important for us humans to understand how it got the answer. This is what everyone talks about as the black box problem. We can see the data we put in and we can see the answer that comes out, but trying to follow the logic through millions of these little connections and on-off switches, it's pretty much impossible for our brains to compute. It's not a list of rules we can read, it's a giant tangled web of math.
And that leaves us with a huge, and I mean huge, question for the future. As we start to hand over really important decisions like medical diagnoses or who gets a loan to these powerful digital brains, how can we trust them? How do we put our faith in a system when we literally can't understand its reasoning? That's a really critical question and something worth thinking about.